So last class we talked about how light can be considered a particle and the experiments that kind of show us a lot of that really kind of epitomizes both the wave-particle duality. But there's this other aspect that shows it as much more of a wave than just the photoelectric effect really does. So the photoelectric effect does a great job of showing both at once. This stuff that we're going to talk about today does a little bit more of a job of showing it as a wave in a really distinct way that we could actually see if we did. So in order to talk about this experiment effectively, I need to give you a little bit more background on what waves are, and specifically what wave interference is. So wave interference is something that you can see. You can see it in waves in a pond or wherever. If you drop a rock into a pond, you make waves, right? You can see the rippling effect going around. And then if you drop two rocks into a lake or a pond, something with relatively still water, you can see these weird interference effects. You can do the same thing if you're out on jet skis and on a relatively calm day, and you can watch the two waves kind of hit each other. This is wave interference. So this is the kind of, you can see it, and you can see you get these interesting patterns that come up that aren't just simple, superpositions of the two. So what do these look like when you do superimpose the two on each other? So there's two different types of interferences. There's constructive and destructive. And if you have waves of a very particular wavelength and they're interfering with each other, you can overlap them right on top of each other or exactly, like cross on each other. And if you overlap them right on top of each other, they add together. If you overtop them exactly opposite each other, they're going to subtract from each other. Now, of course, you could also do some sort of, slight off on it too. But these are the two different ways. So think back to your algebra classes, whenever you had those, and you may have been forced to go through and these had little points on a graph and you had to add them together. And if you added this wave together, you had to add this point and this point. So if this was 1 and this was 2, you'd add them together to be 3. Well, this is 0 plus 0, and so it adds together to be 0. This is -1 and -2, so it would add together to be -3. Same thing over here. Now here only, though, you have a -1 and let's say a +2. We're giving these really arbitrary units. So if you were to add a -1 and a +2, well, that gives you about a +1. And so you would get that, and they would subtract from each other. You might have been forced to go through this in painstaking detail in your algebra classes. We're not going to do that here, but you need to kind of understand how it works. You need to see that, okay, well, if they're over top of each other, they're going to add. If they're opposite each other, they're going to subtract. And that these are called constructive and destructive interference. Now, this is going to be important to understand when we look at this next experiment, which is called the double slit experiment, because you're going to get patterns of light. And these patterns of light are going to be really bright in some places and really dim in others. And that's because you get constructive interference, making it really bright, and destructive interference, making it very dim. And so that's how this is going to work on this next experiment. Now, the best way to show you this next experiment is to have a little video of it. So this video does a great job, and you can watch it as much as you want on YouTube. So I'm going to go through and explain it. He does do the same thing online with words and such. So the way that the double slit experiment works is you have this point source, and you have a place where you can let light through. And so this is sort of showing you how the light would go through, and light expands out like a wave. Now, oops. Okay, we're going to start over. Now, the other thing that you're going to be able to do is you can make the exact same thing on the next one over. So instead of just having one point source, you can have 2 point sources. So you have one point source here, and that's going to let light in at a certain amount. Now you put another light source in another place, or just a hole. One of the easiest ways to do this is to actually just have a light source behind the cardboard or board or whatever and put a hole in it. Now, if you put these together, what happens is that they interact, and you get these interference patterns. And when you come over here, wherever the light interferes in a constructive way, you're going to get really bright, shiny parts. Wherever it interferes in a destructive way, you're not. You're going to get very dim. And you can actually see this. This is a pretty standard freshman physics lab if you end up taking any physics. And it's really, I mean, it looks exactly like this. So this is actually a picture of one from one of these experiments that was done. And it really looks almost identical using the right lasers and things like this. You can actually do this at home if in a slightly different manner. If you take a piece of cardboard and you cut out a little slat and you put 2 pieces of hair and you tape it down and you shine flashlights on it, you can get the same sort of situation where you can get little interference patterns. I used to do it in class, but it was honestly too hard to see in a big lecture hall, so I quit. So, you know, go home and do that. It's fun. You just take 2 pieces of hair, tape it down onto a piece of cardboard, and take a laser pointer and shine it around, and you can see interference patterns too. Now let's look at this a little bit more laid out. So here's the experiment that Young did. He had something that was light blocking here, and he cut one little hole in it to make sure that the light was coherent. And then he shined a light over here so that it came through here. At which point it spread out like this. Now, what that did is it allowed him to have 2 light sources, as what they showed in the other video, but have it come through it exactly the same way. And then at this point, now we had this double split, or this double slit, and it comes through here, it comes through here. And now you have the exact same wave pattern for each slit. But now because they're close to each other, they're going to be interacting with each other. Now, if you then have something over here that detects it, a human eye works just fine to detect it, but you could also actually detect it with, you know, something a little bit fancier. You can see these patterns. So where these interfere completely, you get this really bright peak, and then you get these sort of peaks that get more or less intense as you go through, but you still get these interference patterns. So this is how Young's double slit experiment, or split experiment, worked. So again, now that we've kind of looked at both of these experiments, we've seen how they have properties of both. They can light can act like both a wave and a particle, and it does it at the exact same time. This is called wave-particle duality. We saw that with the photoelectric effect, you actually did see a little bit of both, right? But you definitely saw the sort of particle-like ways that it worked. Where the double split experiment most certainly amplified the wave-like effects. You can't look at that and say, okay, it's not acting like a wave after you've seen that and you've seen those interference patterns. And you know, you can relate that to real life where you see ripples in a pond and you see those interact. And it's very much the same idea. So now this is very true of small particles. So the last time that I had looked, they were able to measure these wave-like properties and things up to 1610 AMU, which is actually pretty big if you think about it. 1,000 grams per mole, you can think of it. So when we say that this is true of very small matter, that's about the size that it goes up to. Now, that's just because that's exactly when we can measure it. So this kind of bridges us into the idea of, well, what does everything have wave-particle duality? I mean, we see it in the small things, but why would an electron have wave-particle duality, but I don't? Why can't I act like a wave? So that's what DeBroglie said, in not quite so colloquial of terms. So he took wave-particle duality from light and said, well, that's true of matter too. And that's true of larger matter to some extent, but we'll see why it doesn't quite work. So what DeBroglie says is, well, wavelength is equal to h, Planck's constant, over p. So depending on how much physics you have, you may or may not know what that is. That's momentum, otherwise known as m times v. This is where font gets us into trouble again, because most of the equation editors like to make it the v kind of like that, which looks too much like a nu. But that is a v, that is velocity. So P is equal to mv, where that's being v. So just said one more time that's quite important to make sure you notice. And you're also, this is more just sort of a general problem solving thing that you're going to run into a lot. You're a lot of times going to be given kinetic energy and asked to find the DeBroglie wavelength. Well, you can do that by finding velocity from the kinetic energy and then plugging that into here. So this takes the wave-particle duality and says, okay, well, that's great, we have it for light, why can't matter have it too? And it gives us an equation that we can actually use for it. So, quick reminder there on your equation for kinetic energy. Okay, so best way to go through and do some de Broglie wavelengths is to do some problems on it. So, for the first one, I say, let's find the de Broglie wavelength of an electron. So something small, and see, I give you the kinetic energy. So since I give you the kinetic energy, we can't just directly fill it into the de Broglie wavelength, because the de Broglie wavelength is h over mv. So we need to find v. So how do we find v? Well, we know that kinetic energy is equal to 1/2 mv squared. Okay, so when we go through and we do this, we solve for velocity, which is 2 times the kinetic energy. So multiply that up, divide by the mass, take the square root. So we can fill in from the problem. Now we get to mass and we say, well, I don't know the mass of an electron. Luckily, this is a homework type problem, so you can look it up. On an exam, and it would just be given to you in the tables. Okay, so we get this. And we get our velocity. Now, something to be kind of careful of here with the mass. It doesn't come up here, or in my other example actually, but it'll come up in your homework and it'll come up on exams. If I have a mass of an electron or a proton or a neutron or anything like that, I'm going to have to give you that mass. If I ask you for the de Broglie wavelength of a nitrogen atom, do I have to give you the mass? Well, no, it's on the periodic table, right? You have the mass. So if you think about nitrogen, are you just going to go through and fill in the mass of, let's say, just an atom? Are you just going to go fill in 14? Well, that's in grams per mole. And if you look at this unit, we have joules, and we need to get meters per second. So remember what a joule is equal to, right? A joule, little sidebar here. A joule is equal to kilogram meter squared over second squared. So we can't have something that we can't put grams per mole in there. So you have to go through and you would have to convert anything from the periodic table into kilograms. So, make a huge note of that in your notes because it comes up and people tend to mess it up. That if you're looking for an atom, you're looking for the de Broglie wavelength of an atom, you're going to be tempted to fill in that grams per mole from the periodic table. You can't do that. You have to convert to kilograms. And not just that doesn't just mean you divide by 1,000 either, right? Kilograms per mole isn't what you're looking for. You're looking for kilograms per atom. So you have to convert from grams per mole to kilograms per atom or molecule, depending on whichever. So make sure you make a note of that, by your mass. Okay, continuing on though. So now we have our velocity, and we can fill that in. You'll notice I sort of changed my units for Planck's constant around. That's just so I can watch all the units cancel. And you get this. And you end up with that for your answer. Now, I always get a few people who ask, well, can't I just take this equation and fill it into here and plug it all in at once? That is perfectly fine. Go for it. Probably it's how I would do it if I were doing the problem. But I think probably 80% of you or so prefer this way, where you do it out separately. So whichever way you prefer, you can do. It doesn't really make too much difference either way. So if you prefer to just fill this equation into here, you are welcome to do that. Okay, so that's the equation for an electron. Now, if we move on a little bit, that's, small, right? An electron, small. You can definitely assume, okay, it's pretty tiny considering, it's an electron, a subatomic particle and all. But what's to say we can't do this for a baseball? So let's do it. Let's calculate the DeBroglie wavelength for something big, something that we can see in real life. Because I'm telling you that an electron has a wavelength, which by that same token, your chair should have a wavelength, I should have a wavelength, my water bottle should have a wavelength. So why don't we see that? Why can't we look at that and see something there? Well, the easiest way to figure out why we can't see it is to, calculate it. So we'll do that. So I give you the mass of a baseball, and I give you an approximate meters per second. Obviously, this is going to change a lot if I throw a baseball or if some famous pitcher throws a baseball. So same rules apply. We're going to fill into here. Again, just for the sake of watching my units, I'm going to just fill in my Planck's constant units in a slightly different way. So we go through, we do the exact same thing we did before. It's a little bit easier this time because I gave you all the values outright. And we get that. So see, baseball does have a wavelength. Now, why don't we see it? Well, think of what a baseball looks like, right? It's, a decent size. You can see that size thing. Now look at its wavelength. Okay, to the -34th meters. That's not something we can see. That's not something that we would calculate. It's not something that we would, be able to look at. And so, sure, maybe by this definition, macroscopic matter does have a wavelength, but it's so tiny that it doesn't matter. And if we look at this equation again, this means that mass is in the numerator, right? Or, excuse me, denominator. So the bigger that the mass gets, what's going to happen to the wavelength? This gets bigger and bigger and bigger. It makes this whole thing smaller and smaller and smaller. So the bigger that something gets, the smaller that its wavelength gets. So you're making something larger, you're making its wavelength smaller, and proportionally it ends up just not mattering anymore. When you had an electron, we had a wavelength of this for something that was very, very tiny. Now we have a wavelength of this for something that's relatively large. And so the wavelengths just start to not matter. So that's what I meant when I said the largest thing that has sort of that we've been able to measure wave-particle duality in. It's that point where our measurements aren't really good enough and it doesn't really make any difference anymore. Something like an electron or a proton or a neutron, it definitely matters for. Something like a baseball, not so much. Okay, so now we get to move on to something called the Heisenberg uncertainty principle. So what the Heisenberg uncertainty principle says on one level is that it's impossible to simultaneously know both the momentum and the position. So with absolute certainty. So it puts a limit on how well we're able to know this. It says that if you take the uncertainty in x, so notice that's not x, it's the uncertainty in x, the part that we don't know about where the position is. So, in really crude terms, maybe if I take a guess and I say, I'm 3 meters away from that door. I'm not very good with estimations, so my delta x might be a meter. Maybe I measure it now and I say, well, now my uncertainty, I measure it and it's really close and I'm actually 3.5 meters away. And I can say, okay, well, I'm pretty sure of that within plus or minus 4 centimeters because my measuring isn't very good. I use, a cheap measuring tape. Now maybe I measure it in a stand in one place and I use calipers and I'm really careful and I know it within a millimeter where I am. That's what an uncertainty would be. It's how well you know where something is. This comes into play much more, this is really more talked about with small things, electrons, protons, things of that sort, but that's how you want to think of it. Momentum is going to be the same way. Now, assuming that, keeping in mind that momentum is mass times velocity, a lot of times you'll just see this as mv, because you assume you know what the mass of the particle is. You assume you can look that up and you can weigh that, and that's pretty perfect. So what happens if your momentum in uncertainty decreases? Let's say you're using really, really good equipment, because do notice that this is greater than or equal to, meaning that it's got to be greater than that. That's the lower limit, but it might be more. It might be that your uncertainty in both are huge because you aren't using very good equipment. But according to this, even the best equipment in the world, which arguably there may be some people who have published things saying that they may have broke it. We'll see how that works. But according to this, you can't. And if this happens, so let's say best instruments, you're right at that Heisenberg uncertainty principle limit. If your momentum uncertainty decreases, well, what does that mean for your position? Well, if the uncertainty in your momentum decreases, if you measure that better and better and better, that means that your uncertainty in your position will increase. So every time you improve one, you lose the other. So you can improve this, you can know where that particle is at with a little bit more certainty, but you're not going to know its momentum very well. And you can get better and better and better at knowing its momentum, but you're not going to know its position very well then. So what happens if your uncertainty in position decreases? Well, then your position, your other one is going to increase. So it's always this back and forth. You decrease one, you increase the other. You decrease that one, you increase the other. Okay, so this problem is based off a commonly told and really bad chemistry joke. So the joke goes that Heisenberg is driving along and he's pulled over by a police officer, and the police officer comes up to him and he says, do you know how fast you were going? And he looks at the police officer and says, nope, but I know exactly where I am. So the joke there being that you only know one or the other. So I want to try to prove whether or not we can use this. If, I'm driving to work, arguably probably too fast, and I get pulled over, can I argue with the cop on the thing that, well, he knows where I am, so he can't know how fast I was going? Obviously, there's, some sort of quantum system here that he can't write me a ticket. I don't think I would suggest this argument anyways, but let's see if it's actually valid. Let's see if it holds up. Okay. So we're starting from this equation on the slide, which is to say delta x times delta p has to be greater than h over 4 pi, or equal to. So that's our limit. Now, of course, it can be more, but it's got to be equal to that. So let's rewrite this a little bit differently so that we have velocity there. We're going to assume I weighed my car and I know exactly how much it weighs. Since this is a little bit of a back of an envelope calculation. Okay, so I tell you that, I think that the officer should be able to measure where my car is by about half a meter. And I know the mass of my car to be 1,300 kilograms. So we need to solve for delta V. So we can see whether I can argue myself out of a ticket this way. So let's first solve for delta V. And then fill in everything that we need. Okay, so if we do this, we get a delta V. Our delta V has to be less than or greater to according to the quantum mechanics, this. Okay, so now, can I argue to the cop that I shouldn't get a ticket? No, right? My delta V here is tiny. So according to quantum mechanics, he knows how fast I was going times 10 to the negative 38 meters per second. I promise you I was speeding by more than that. So this quantum mechanics limit isn't an issue here. So this, it's a silly example, but it does show how you would go through and do it for any other particle. You would just have a different mass. So same rules apply here, has to be kilograms, right? So grams per mole isn't going to cut it. You need to change it to kilograms per atom. If I give you the mass in grams, you need to make sure you convert it to kilograms. So same rules apply here for any sort of subatomic particle, but it's a little more fun to try to calculate this way. So this is not a good way to get out of a ticket when you get pulled over. Even if your particular police officer does have a strong background in quantum mechanics. Okay. All right, so next thing that we're going to talk about then. This seems to be every freshman's favorite topic in chemistry. So wave functions, energy levels, and particle in the box. So this sort of sets up this next big section of this chapter. We've sort of talked about all the history and the basics to get us to this point where we can start building up a molecule. We can start building up a hydrogen atom, and then we can move on to multi-electron systems, and we can move on to diatomics. And at that point, we'll kind of skip some steps and just have molecules. So what a wave function is, it's represented by this psi, which is another Greek letter. And it's going to describe the movement of a particle, okay? So it's just a symbol for a mathematical function. So I'm going to show you those functions in a little bit. We're never really going to have to work with them. I'm going to give you the solutions that come out of them. I'm going to give you the pictures that they pull out of them. You need to know the general way in which these work, though. You need to know that it describes the movement of a particle. You need to know that it is a function that you can actually graph, that they've solved these functions and they can put them into a computer and they can graph them, and that's what gives us our orbitals. Different particles are going to have different wave functions. So a particle in a 1s or in a 1s orbital isn't going to have the same wave function as a particle in a 2s orbital or a 2p orbital or all of those. Now we have something called psi squared, or the probability density. Now what this is going to give us the probability of finding a particle in a particular region. So if we say we want to find the particle from here to here, what is the probability that it's going to be there? And that's what the probability density, what we can gain from it. Now, keep in mind, if wave function, or psi, is a mathematical function, what is psi squared? Well, it's that function squared. So that's why it's called psi squared. So technically, the probability density is the probability of finding a particle divided by the volume. So that's just sort of a technical thing to make the numbers work that I wanted to add here, but don't worry about that too much. So let's go through and talk this out with like a super simple example, not something that would actually be a wave function, but it gives us a little bit more of a clear way in which how these bigger functions that I'm going to show you work. So this is more understanding purposes and being able to replicate it purposes. So let's take an example where psi is a number. I do this to make it simple, right? How can you get a simpler function than a number? So we're going to say that psi is just 0.44 centimeters inverse. So your book walks you through this sort of idea too, but I wanted to go over again. So if we graph this function, the 0.44 centimeters inverse, we get this. So, well, what's psi squared going to be? Well, it's just 0.44 times 0.44. So we can graph that too. All right? Again, really simple examples. These wouldn't be wave functions of something we'd actually calculate, but it gets our point across. So this would describe the movement of the particle. This would describe the probability of us finding it in any particular place. So the wave function, this is sort of nomenclature, how we would say this. The wave function is equal to 0.44 centimeters cubed, or inverse. The probability density is equal to 0.2 centimeters cubed. So if I wanted to know what is the probability of a particle being within 0 to 3 centimeters cubed? I say, what is the probability of me finding this particular particle between 0 and 3 centimeters cubed? In other words, between here and then 3 centimeters out from it in a circle. Well, the probability of that, you would just multiply this together, right? It's effectively taking an integral, but it's a simple integral because it's a box. It's just the 3 times by the 2. So our y-axis times by our x-axis, since it's a box. And that would give us our probability density. Now, this is a very simple example with a very simple function. When we do this with bigger functions, we're going to get much more complicated probability densities and different shapes and things of that sort. But this is how they do it. They just do it with a computer instead of by hand. So let's look at some things about this. So some questions for you. Psi is a function. So at any point, can we determine its sign? Meaning positive or minus. Does it have to be positive? Does it have to be negative? Can it be both? Well, it's just a function, right? So sure, the function I showed you in the last one was always positive. We agreed that was sort of a simple example. Wave function, it's just a function, so it can be both. It doesn't matter. The sign doesn't matter. So if I show you a graph like the one on the other slide, like this, and I say, well, which one's the wave function? You would know that it's the one that can be negative. This one. Now, if we move on to psi squared, and I say, well, the square of that function, right? It's just taking the function, squaring it. So if you square something, can that ever be negative? Assuming that we're in the realm of real numbers. Well, no. That's got to always be positive. So if that's always positive, if I were to give you a graph like this one, and I say I have both the probability and the probability, or I have the wave function and psi squared graphed, you could pick out which one was which. You could say, well, this one's negative, so it's got to be psi. This one's always positive, so that one will be psi squared. Okay, next thing to talk about then is nodes. So nodes occur when psi is equal to 0. Now, if psi is equal to 0, what does that mean about psi squared? That was going to mean that psi squared also equals 0, right? 0 times 0 is most certainly 0. So wherever wave function is equal to 0, psi squared is equal to 0 as well. Now, think about what psi squared is, though. It's a probability density. So it's where you're likely to find something. So at a node, what's the likelihood that the particle will be there if psi squared is 0? It's going to be 0. Right? Because if the psi is 0, that means psi squared has to be 0, and psi squared is probability density. So if the probability of finding a particle someplace is 0, it's not going to be there. So wave functions have n-1 nodes. That may not mean a lot to you right now, but when we start talking about energy levels, that'll mean a little bit more to you. So if we have a wave function at a particular level for a particle in a box, it's going to have n-1 nodes. So here, we don't really have a node. Technically, this is asymptotic, so it just approaches 0, never quite hits it. And you talk about nodes just being in the center, like right here. So this is asymptotically going to 0. It's not a node. This is a node. OK. So now, Shrodinger equation. This is where we really get into all of your guys' favorite things. So what the Shrodinger equation does is it allows us to take the wave function and come up with an energy level. Now, we've talked about energy levels already, right? We've talked about the Bohr model, and we've talked about having an n equals 1, and an n equals 2, and an n equals 3. It might be an oversimplification of energy levels, but it does work to help you kind of think about it. So the Shrodinger equation gives us a way to actually go through and find these energy levels. Now, you don't have to worry about this equation so much. I put it there mostly because your book does, and it's good to have seen once. If you go on in physical chemistry, you'll see it a lot. But the way that this works, the way that this equation works, this H is called an operator. And what that means is that you're taking something and you're doing something to this function. An operator operates on a function. So for those of you who have had some calculus, which is most of you, that means that, for instance, if you take a derivative of something, if you take the derivative of sine, or you take the derivative of cosine, that taking a derivative of is an operator. Maybe it's something simpler, maybe it's plus 2. So you take whatever function you have and you add 2, and that's your operator. It just means you're doing something to that function. So this happens to be the H, the operator. This is what the hat means. This happens to be what we call the Hamiltonian, and this is the Hamiltonian for this, okay? Now, if you care, this is one of those for your info sorts of things. This is the double derivative, right? So that would mean you take the wave function and you take the double derivative of it. You multiply it by this. This is just a number, right? It's a big equation, but this part is just a number. It's h bar, which is h over 2 pi. It's just a constant squared. 2m, which is just a constant. So you have that, and then taking the double derivative of it. So again, you don't need to worry about this too much. It's just sort of for your info. The part you do need to worry about is knowing that this is a Shrodinger equation, that this means you have to do something to the wave function, and then you get your energy back. So one of the easiest ways to think about how this would work is if you take the double derivative of a sine or a cosine. If you take the double derivative of a sine, you end up back with sine, but now it has a -1 in front of it. This would be like this. You get the same equation back, but you have some number in front of it. So taking a double derivative of a sine would give you negative sine, and you would get the -1 back. If you don't have any calculus, it's a little bit harder to come up with the way this would work. So we'll just kind of leave it at that. But you have to know that you have an operator, it operates on a function, and you get an energy level. That's sort of the condensed version of what I want you to know for this class. So the way that we're going to use this is we can use this to find the wave function in E. Now for this class, we're just going to use the results of this. We aren't going to go through and do this. We aren't going to calculate these. We're just going to say, okay, and here are the energy levels. Here's the results. Okay, so we're going to start with a system called a particle in a box. Now this got started with because it's a little bit simpler than something like a hydrogen atom. Hydrogen atom has sort of 3-dimensional space. A particle in a box is simpler. So the way that this works is you have a box. You can think of it as a box. And the electron can't go through the box. And it's in the middle. It has to be inside the box. And it's going back and forth, which is a little bit not quite the way you want to word it, but it's in the box. So kind of the real life way you can think about this, since it's hard to picture an electron being delocalized in a box, is if I took a string and I stretched it from room to room and then made it like a guitar string and plucked it, and you have this wave going back and forth. So, go home, steal someone's guitar and look at, pluck the string, see what happens. You'll be able to see the wave kind of oscillating back and forth. Now, you're allowed certain wavelengths. This is relatively easy to do with something like a jump rope, right? You can take a jump rope and you can very slowly go like that, and you can get this pattern. Or you can speed it up. And when you speed it up, you can get a sort of pattern like this. And the faster you go, the more times you can get it to oscillate in one. Eventually, your arm won't be able to do anymore, but that's not an issue with the particle in the box system. So that's how you can kind of think about this working. Now, you'll notice only certain wavelengths are allowed. Same is true when you go through and try to do this with a jump rope, right? You're allowed the certain wavelength where you get this, the certain wavelength where you get this, but not in between. And when you try to switch from going the slowly way to a little bit faster, there's this weird point where you get this, it's not a wave anymore. It's not a normal wave, a transition point. So it kind of works there too. Now, here's where we're going to take the Shrodinger equation, and I'm just going to tell you what the result is. So that H psi equals E psi, the H psi equals E psi, and I told you that we're going to just solve for E, and I'm just going to tell you what it is. Okay, well, here's our results. So this is psi. This describes the different equations that can relate this electron in the box. And then this is our solution to the Shrodinger equation. This is our energy. Now, don't let this equation bother you. There's a lot of things in it, but none of them are that big of a deal. N, that's just 1, 2, 3, 4. If you're thinking about your jump rope, that's which level of energy it's at, how hard you had to move your arm to get that. Now, H, Planck's constant, right? It's not any different than what we've been talking about. 8, I think you're okay with the number 8, hopefully. And we have M, that's the mass, so just whatever particle we're talking about. And then L is the length of the box. So that's not a big deal either. That's just a number that we're going to decide on for any particular system. It's just from here to here. Okay. So what we can do is we can kind of use this to model a particle in the box example where we're given a wavelength of an electron, or we want to find the wavelength of an electron of a theoretical atom given an approximate diameter. If we say that the diameter is about 100 picometers, and we can find the wavelength of that theoretical atom. So I've changed this example around a little bit from what was on the slides. So this is what was on the worksheets. And I say we're going to go ahead and we're going to solve for this. So actually, I've just decided to skip this. Forgot about that. We decided to skip that and do that at a later time once we know a little bit more about the way quantum mechanics work. I think it'll be a little bit easier to understand then. So in the meantime, let's now take and go to the next step. So the particle in the box is a nice model. It kind of lets us take, if you actually go through and do the quantum mechanics, it's a little bit easier to work with than something like a hydrogen atom. The equations are simpler. So that was kind of why it was developed. But now we also have hydrogen atoms. And we can actually go through and we can find the equation for that. Now, I'm going to talk about two different ways about thinking of all of this with the hydrogen atom. We're going to talk about the Rydberg equation. And then I'm going to go through and do it with the Shrodinger equation as well. Now, the results of these are exactly the same. So what you're going to find is regardless of which way we do it, you're going to have the same answer and we're going to have the same equation. So you can sort of pick the easier of the equations when you're trying to solve for an actual number here. So in my opinion, I think the Rydberg equation is probably easier to work with. Now, both of these were used to describe the hydrogen atom, but the difference is in how they were discovered. Rydberg did it experimentally. He looked at a whole bunch of spectra coming in and said, noticed patterns and noticed the way numbers work together and came up with an equation that described it. And it had a constant in there that we're calling the Rydberg constant, and it had all of the energy levels and everything in it. Now, what Schrodinger did is he said, well, I'm going to start from, the wave function, and I'm going to put the Hamiltonian on it, and then I'm going to solve for the energy, and then that's going to give me all of the energy levels. So one was done experimentally, one was done theoretically. But either way you do it, you get the exact same results. So Rydberg's was done first, and then Schrodinger's agreed, which is always great. In science, that's what you want. You want someone to do it experimentally, and then someone to do it theoretically, and have the two results agree, because that means that your theory is relatively sound. If your theory doesn't agree with your experiment, or your experiment doesn't agree with your theory, you're obviously not understanding something. So this showed that they both kind of had it right. So this is going to be true for the hydrogen-like atoms. And what I mean by hydrogen-like atoms is one-electron systems. So if you take some sort of atom and you take away all but one of its electrons, you can use this solution set to do it with one little change. Now, I'm going to start backwards from reality and start with Schrodinger, because I think having the theory base first and then working into the experimental is a little bit easier to understand. So with Schrodinger, this is going to walk through and do the exact same thing that we did with particle in the box. So now remember I said I was just going to give you the results. So this is the results when you come out. This is the energy level. Now Z is equal to the atomic number. So Z is one of those letters that is kind of universal in chemistry, and so you want to recognize that as atomic number. H, Planck's constant. We'll talk about R in just a minute. We'll leave that alone for a sec. And then N is the energy level. So now what R is this whole series of equation, or this whole series of constants. None of these are a big deal. They're all just constants that you can look up. It just gets a little tedious to write them all in. So you just have a ton of constants here, and then the z squared h over n squared. So really, h is a constant too, right? So you really just have z squared over n squared times a whole bunch of constants. So keep that in mind when we go to do Rydberg's equation. It's really just z squared over n squared times a whole bunch of constants. Now, let's look at the Bohr model of the atom one more time. So remember, we have our nucleus with all of our positive charges, and we have our rings of electrons going around the outside. Now, this arose because they knew that we had a proton-filled nucleus, and we had the electrons going around them. Now, the interesting thing here is that if you look at the laws of physics, it says that the electron should spiral into the nucleus, that it should be going around and around and around and then just spiraling in and everything collides in together. Well, after Planck discovered quantization, and Planck said, hey, these particles are emitting at all different sorts of wavelengths, and they're very particular wavelengths and not in between, Bohr said, oh, well, that's because the energy levels are going to be quantized, that you can have this energy and you can have this energy, but you can't have an energy in between the two. Now, this particular model is only going to work for one electron systems. It does turn out that they're quantized just in a slightly different way than what Bohr thought. Now, the energy difference is given by negative RH z squared over n squared. And that's what Rydberg went through and said. So before we talk about exactly what Rydberg said, I think it's kind of worth noting the Stair and ball analogy for quantization and energy levels. The idea here is always that if you set a ball down on this energy level or this energy level or this energy level, it can be at any stair step energy level. It's never going to be in between. It can transfer between the energy levels. It can go from here to here, but it cannot be like held in the middle somewhere. It needs to be on one of these particular levels. So that's sort of how you want to think of these, is you can be here, but you can never be in between. Okay, so now moving on to what Rydberg said. Rydberg looked at all these sorts of spectra that we're going to talk about in a minute and said, well, this is what I think the energy levels are at. I think that it's at some constant that I'm going to call the Rydberg constant because my name is Rydberg, and so I like the way that sounds, times z squared over n squared. Now, keep in mind, what did we have for Schrodinger's equation? We had a whole bunch of random constants that all have numbers associated with them, times z squared over n squared. So the two aren't any different. The only difference is that when Bohr did it, he just knew it was a number. He just knew, because experimentally this had to be a number, and he just called it one constant. Where Schrodinger, because he did it theoretically, was able to say, well, I know what all those constants are. I know that they're, it's all of these combined together. If you multiply all of those together, it comes out to be the Rydberg constant. It comes out to be the same number. And so that's how these two are related. I think that this one's the easier one to work with because we only have to worry about one constant as opposed to those like 5 or 6 different constants. Okay, so that's our energy level. Don't forget Z's atomic number. So we're still always going to be talking about one electron systems, but because we can have ions, Z can change. We can have a helium 1+ or a lithium 2+ or things of that sort that we're calculating. So this is what the Rydberg constant turns out to be. There are some other versions of the Rydberg constant that you'll see. A lot of times you'll see it written in terms of Hertz, and you'll see the Rydberg equation that we're going to talk about in a minute written a different way as 1 over lambda. The way I'm doing it on the slides is the way that I've found the least amount of people to make mistakes on actually doing the problem. I would suggest doing it this way. Your homework suggests doing it a different way. I don't remember what your particular book says. There's like 4 or 5 different ways to do all of these problems. I think this is the best way to not make mistakes at your guys' level. So Z is, again, your atomic number. Drive that point home. Okay, so what is our energy difference? So we're going to care a lot about these transitions. How much energy it takes to go from this level to this level. How much energy we get back if instead now it drops down to this level. And we're going to want to be able to calculate all of these. You can do this with both Schrodinger's and Rydberg's equation. But again, Schrodinger's is a little bit complicated because of all these different constants, where Rydberg only has R. So it's a little bit easier to work with. So we're going to go through and we're going to work with Rydberg's. So if we want to find the difference in energy levels, the difference that it takes for an electron to go from here to here, or from here to here, or so on, it's a difference. So it's always final minus initial. So we're going to go through and we're going to derive this as sort of our last thing of the day. So for a given energy level, it's going to be defined by this, right? This is just from the last slide. So we know that we can find the difference in energy by taking the final and subtracting the initial. That's just the definition of change. Now, we also know that we can define both states. We can define the initial and we can define the final. So all I did was rewrite this equation 2 times. One time calling it arbitrarily initial and one time calling it final. Now we can fill these in to this equation. So we're going to take the final and fill it in. We're going to take the initial and fill it in. So change is equal to final minus initial. So we fill everything in. So again, taking the energy levels, filling it in. So we're trying to find the difference in energy between 2 different levels. Now, we have RH, which doesn't change, and Z, which isn't going to change either, right? Because it's not switching atoms, it's just switching within one atom. So we can just factor those out of the equation, set them aside for the sake of algebra. So when we do that, we get these, where we take and we have the RH and the Z squared. You can factor the Z squared out too. Some books will leave it in, some books won't. You end up with this equation. Now, something that gets talked about a lot and students have issues with is the fact that this is written 2 different ways depending on where you happen to find it. Sometimes you have a negative sign and sometimes you don't. So the difference here is that here you have a final minus initial and you factored out the negative. Here you basically put the negative inside, but when you did that you ended up with initial minus final. It doesn't really matter which one you use. On the final, I'm going to give you one of them, so just use that one. But when you're doing your homework, be careful if you're doing this off memory not to mess this up. The one with the negative is final minus initial. The one without the negative is initial minus final. And it's not that one of them is wrong or one of them is right. It's just different ways of writing the exact same thing. So keep that in mind. So next time we'll go through and we'll do some examples using this, and we're going to do a lot of talking about sign convention because the signs for all of these are really important and honestly is one of the most commonly missed things on the entire exam. If you mess up the sign, you're going to have problems. Again, going back to what I said before, there's different versions of this equation. You'll see it with 1 over lambda. Sapling does that. Some books do that. I think it's easier to do it this way. And I'll show you why when we go to worry about sign conventions and we do some examples. You have to be really careful about which direction these transitions are going. Delta E is going to be allowed to be positive or negative, and you're going to run into problems if you mess that up, if you mess up whether the delta E is positive or negative. So we'll talk about all that next time, all the sign conventions, examples, things of that sort, and really kind of finish up the hydrogen atom next time.